So hello students, welcome to the class. This is the third class of electromagnetic theory. Okay, so in the first two classes what we have learned uh, what the Maxwell equations look like in vacuum or free space, and then the uh, wave equation, okay, electromagnetic wave equation, then the properties of the electromagnetic wave, right? All three properties we have learned. And in this today's class, what we are going to do, we are going to find what the Maxwell's equation look like in matter. Okay, that means in dielectric medium. Okay, so let's get started. So as we know, these fours are what? All these four are Maxwell equation in free space or vacuum. Okay, so now let's see what this first equation will look like in dielectric medium. Let's get started one by one. Okay, so let's go to the first. Okay, so now in free space, what we know that del dot E equals to rho by epsilon naught. Okay, so this is the charge density. But in free space, there was no concept of actually free charge and bound charge. Okay, that means in vacuum. Okay, all those charges were free. But now in case of dielectric medium, there will be the concept of free charge and bound charge. Okay, so rho is the charge density. So charge density will be the summation of free charge density and bound charge density. Okay, so I am writing it down as rho will be equal to rho free plus rho bound. Okay, so what is the concept of free charge and bound charge? Okay, so in metal all the electrons are free, they can move anywhere. Okay, so those are free electrons. Okay, so let me write it down. Electrons in metal are free. Okay, those are what? Those are free. Okay, so the charge density will be what? Free charge density. Okay, so that will be rho free. Okay, but now in dielectric medium, let's say about as we know in semiconductor, okay, the electrons are bounded. Okay, so let's say silicon semiconductor. Okay, let's say it will be p type. Okay, that means it is doped with, let's say, aluminum. There will be 3 electrons in the outermost shell. There will be 4. Okay, again this is silicon, 4 electrons will be there. Okay, and there is also an silicon, 4 electrons will be there. Okay, if we are going to apply an electric field from this side to this side, okay, this side to this side, then what will happen? There is a point. Okay, this is what positive charge carrier. Okay, and these electrons are what? Negative charge carrier. So on applying this electric field, what will happen? This electron will move to this place. So this will be filled by an electron and there will be a void. Okay, and this void will be again okay, the electrons from this silicon will move to this place and now the void will be here. So in this way the electron are going to move from this side to this side. Okay, electrons are going to move from this side to this side. So as electrons are moving towards this side, so there will be a charge in this side. Okay, so these charges are what? These charges are bound charges. Okay, so the electrons can't go anywhere. Okay, they are restricted to move only through these sides. Okay, this side, this side, this side. Okay, so they can only move through these sides. Okay, so these are what? These are bound charges. Okay, and the charge density will be what? Bound charge density. So this is the concept of free charge density and bound charge density. Okay, so now what I am going to do, now I am going to take this epsilon naught towards the left. Again, this epsilon naught is what? This epsilon naught is a constant, so I can take it inside of the divergence. So I am writing it down as this. Okay, so now what is in the next step, what I have done, I have done this. Okay, so I have replaced rho bound by minus divergence of p. Okay, p is polarization. So now what I am going to do, let's say let's elaborate this. Okay, so let's say this is an dielectric medium. Okay, this is totally okay, electrically neutral. Okay, so if I am going to apply an electric field, okay, from this side to this side. So what will happen? So initially, what the center of the negative charge and center of the positive charge what was coinciding, right? So this uh, is the center of positive and negative charge, okay. So they were coinciding, but as soon as we apply this electric field, what will happen? The negative charge will move towards left and positive charge will be moved towards right, okay. So there will be an what? Polarization of this matter, okay. So the polarization can be written as P. So the negative charges have got displaced by a distance or by an amount towards left, and the positive charges got displaced towards right, okay. So this is the polarization. So as soon as we have applied this electric field, so negative and positive charges got separated, okay, uh, like this way. So in this space, what we get? We get some charge densities, and in this place also, what we have got? We have got some charge densities, okay. So these are what? These are bound charge densities, okay. We have got this charge densities because of what? Because of this polarization, right? So these bound charge densities can be written as rho bound equals to minus divergence of the polarization, because this bound charge density, how we got this? We got this because of this polarization, right? So I am replacing rho bound by minus divergence of polarization in this step, okay, from this to this, okay. So from this step, now all these things are simple, okay. So now let's move this towards the left. So this negative sign will be converted to positive sign. So this is positive, and on combining these two terms we will get this, and this will be rho free, okay. And this is what? This is displacement. D is what? D is equals to epsilon naught E plus V. E is electric field and D is displacement field, okay. So what we have got? We have got divergence of the displacement field equals to rho free. So this is the Maxwell's first equation, okay. This is the Maxwell's first equation in dielectric medium. And the second one remains same, and the third one also remains same, okay. So this is del dot B equals to 0 and del cross equals to minus del B del T. And the fourth one, there is some change, okay. So what was the fourth equation? The fourth equation was del cross B equals to mu naught J mu naught epsilon naught del E del T, okay. So here I am going to ask you one question, okay. The first equation will be changed and the second equation will also change, okay. But the second and third one, these two are not going to change. So what is the reason, okay. So what is the actually difference in the free space of vacuum and in dielectric, okay. So in this dielectric, what we have got? We have, okay, this is the rho free. Rho is, that means the charge density. This is only free charge. When we are going to talk about vacuum or free space, there is only free charge, okay. But in dielectric medium, what we get? We get both free charge density and bound charge density, okay. And in the first equation, there is somewhat charge density term. Again, this is what J is current density. And this current density again can be arised because of free charge density rho free plus what? Rho bound charge density, okay. So this equation also contains some charge density term, right? And this also contains, first equation also contains some uh, charge density term, okay. So only first and fourth equation will change, but second and third one will remain same, okay. We have already we have discussed the first one, the second and third one will remain same, and now let's come to this fourth one, okay. So let's move forward, okay. So current density is what? J, okay, we represent it by j. Okay, so now what I can write, I can write j as what, okay, this is not here. Okay, so J is the total what, total current density, and it is the summation of free current density and bound current density. Okay, so J free, I have used some abbreviation for free current density. I have write it down as JF. Okay, and for bound current density, what I have written J bound. Okay, and J bound equals to what, let's say JB. Okay, for bound current density, this will be equals to del T of P plus del cross M. Okay, so okay, how these terms arises, I will talk to you about this later. Okay, in this video. So this is the main concept. Okay, how we have got these two terms. Okay, so now you just assume that JB can be written as del T of P plus del cross M. Okay, so now let's put this j term. Okay, j equals to this, right? So let's replace this in what, fourth equation. Okay, so what is the fourth equation? Del cross B equals to mu naught j plus mu naught epsilon del E del T, right? So j can be written as jf plus del cross M is here, and plus del P del T, right? So here is also mu naught, here is also mu naught, right? So now let's take it towards left, to the left. So on left, this will be in the denominator, right? So again, this is a constant term, so I can take it inside. So here in this step, I have taken this inside. So now what is this? This is jf del cross M del P del T, and mu naught is here. Okay, and epsilon naught E T, right? Del E del T, right? So by on combining these two terms, what we will get, del T of epsilon naught E plus P. This is what, this is the displacement field. Okay, and this is JF, and this is del cross M, right? And del cross M, if we move this towards left, what we will get, we will get a minus sign here, right? This was positive here, so we'll get a minus sign here. So, and what I can write, I can write that H equals to B by mu naught minus M. Okay, so del cross H equals to J free. Here in the right side, what we will get, we will get only J free and del D del T. This is what D equals to epsilon naught E plus P, as we have discussed earlier. Okay, so these are the two terms. Okay, so del cross H equals to J free plus del D del T, and these two terms. Okay, this step, and in the first Maxwell equation, this equation. Okay, how we get this? Okay, these are not actually properly clear. Okay, so now what I am going to do, I am now going to clarify these things. Okay, so we all know D equals to epsilon. This equation we all know, right? So actually this equation came from this term. Okay, this equation. So what we can write, D equals to epsilon naught E plus P, right? So and P can be written as what, epsilon naught E plus epsilon naught chi E plus this will be E. Okay, so let's take it common, 1 plus chi E plus E, right? So now what we will get, this can be written as epsilon. So I hope now these things are clear, how we have got this equation, and we also know that B equals to mu H, right? We know this equation, right? So actually this equation came from this. Okay, so now what I can write, I can write B by mu naught minus M equals to H. This is M. So B by mu naught equals to H plus M. Again H plus, this is J, this is M. Okay, this will be what? This will be H, right? So now B equals to this will be here, it was in the denominator, so this will be on the right hand side, this will be in the numerator, mu naught, and on taking H common, 1 plus xi m equals to H. So now what I can write, this is mu H, so B is equals to mu H. So actually these two equation, this and D equals to this, these two equations came from these two, okay, this one and this one, right? I hope you have understood this. Okay, so now in the earlier what I have told that you just remember this, okay, JB equals to del P del T plus del cross M. So actually how this how we have got this, okay, so now let's talk about it. So we all know the continuity equation, right? So what was the continuity equation? Del dot J plus del rho del T equals to 0, right? So this was the continuity equation, right? Equation of continuity. So actually in your basic examination, these are okay, these things are not so much important, okay, actually this, okay, if you just remember this, okay, this term, then you will be able to answer all these questions, okay, and this derivation is also limited to this portion, okay. So the main concept here, so this is the equation of continuity, right? So this row doesn't indicate that this is the free charge or bound charge, okay. So if we are going to replace this row by row bound charge, okay, so then the equation of continuity also be satisfied, okay. Then the current density will be what? For bound charge density. So if we are going to replace row by what? Row bound, that means bound charge, then what will happen? The current density will be also because of what? Bound charge, okay, plus del rho b del t, right? If we are going to replace this by free charge, okay, rho 2 by free charge. If we are going to only talk about free charge, okay, let's say this is some dielectric, okay. So if there are both bound charges and free charges, okay, 3 plus both bound. So if rho equals to what? Rho free plus rho bound, okay. So if we talk about the total charge density, okay, that means rho, then this equation is like this, okay. If we are going to only talk about bound charge, okay, then the equation will look like this, okay. Then the current density will be only because of bound charge. We will consider the current density because of only bound charge. And if we are going to talk about only free charge, then we are going to we will only have to take the free current density, right, plus and the, okay. So the equation will look like this, right? So I hope you have understand this, okay. So now I am going to talk only about what? Bound charge density and bound current density, okay. So as we know that the bound charge density can be written as divergence of polarization, right? I have taught you this earlier in this section, right? So this is the what? This is an dielectric medium, and here the center of the positive and negative charges were coinciding, right? And then if we apply some electric field, then the center of the negative and positive charge got separated and we got some bound charges densities, okay. So this will look like this. So rho b can be replaced by what? minus divergence of polarization. So if in this equation, what I am going to do, if I am going to replace this, then what I can write, okay, this equation, del dot jb plus, okay, del t of minus del of p equals to 0, right? So this is the step, right? So what I can write, divergence of jb equals to, let's take this approach, right? So what I will get, the negative side will be del p del t, right? So what we can write, jb equals to what, del p del t, right? So jb can be written as del p del t. So this, okay, but here as you can see, I have written jb, that means bouncers, not only this term, okay, jb equals to not del t of p, there is an extra term, okay, del cross m. Why I am adding this term, okay? So let's talk about this, okay? So now let's take this term, del dot jb equals to del of del p del t, right? But we all know that divergence of curl of any vector is 0, right? So I am going to use this property, okay? So now I can write a here, I can now add a term here, okay, then cross m, okay. So I can add this term here. Why I am taking the magnetization factor, I will tell you, okay? But now let's combine these two terms. Okay, right? So what I can write, jb equals to del p del t plus del cross m, right? So I can write this. So from this I was writing this, okay, bouncers for jb, I was writing this, okay. But now why I am taking only magnetization factor, right? So I am going to tell you that, okay, because it is not sufficient to represent bound currents in material media, that means in dielectric medium, as simply del p del t, okay, only this term, because bound carriers can also conduct divergence free current, right? This is actually divergence free current, okay. Let's say one current is okay in circular conductor, okay. In this circular conductor, if there is a current I, this is divergence free current, because this current is in closed loop, right? In this closed loop, the current is divergence free, okay. And in medium, okay, that means in dielectric medium or in any medium, electrons orbiting in the atomic nuclei, okay, and this is the atom, okay, this is nucleon, the electrons are orbiting in this direction, okay. So there is a current, right, in this direction, in the opposite direction of the motion of the electron. So these electrons orbiting the atomic nuclei, they produce such divergence free current loop at microscopic level, right? Okay, if this is an dielectric medium, there are many more, okay, many more atoms, right? There are many atoms, okay. So if we are going to consider a very little here, a microscopic part, so in that part there will be an divergence free current because of the circular motion, okay, the motion of the electron, because of the circular motion of the electron, because the electron is orbiting in a closed loop, so the current is what, divergence free, okay. And these divergence free currents can be represented by the curl of its what, magnetization, okay. So this is the magnetization current term. This is what magnetization current. Okay, this is the magnetization current. So this is the actually main concept why there are these two terms, not only this term. Okay, so this term comes from this concept. Okay, magnetization current. So what is magnetization current? This is the current due to the circular motion of the electron in its in the orbit of the atom. Okay, and this is what this is divergence free current. Okay, divergence free current. Okay. Actually, even a let's say this is an electron. Okay, this is an electron. Okay, this is an electron. It's not moving. Okay, but due to its intrinsic spin. Okay, due to its intrinsic spin, uh, it contain okay divergence free current. Okay, it's contain divergence free current, right? And this is because of its intrinsic spin. So I hope you have understand these things, right? So how we got these two terms? This is the main, actually main concept. How we have got these two terms. This one and this one. Okay. So this is the end of the today's class. Thank you.